Hi everybody, welcome again. We still in the third section. We have some additional two examples. They have different ideas than the examples what we solved previously. Starting with example number 4, we have two systems. They look like each other. Each system has two charges. The first system has Q1, which is 2 microcoulomb, and Q2, which is negative 8 microcoulomb. The second system is the same, but the second charge is positive 8 microcoulomb, and the distance between the charges is the same 1 meter in both cases. Now, for these two systems, we need to use a test charge, which is 1 millicoulomb. Milli means 10 to the negative 3. Now, we need to use this positive test charge in the both systems to find the balance. The balance means the total forces on this test charge is 0. Total forces from where? We have two charges, and we need to put this charge in a position in each system, and at this position the total force on this charge, which is the test point, should be 0. Let us start with the first system, which has positive and negative charge. Then later we will solve the second system, which have two positive charges. Okay, now we can have some analysis or understand our problem before starting solving, which will be easy. We can do that. Assume that we have the negative charge and the positive charge. There is a distance between them. This distance is 1. We need to put the test charge, which is a positive 1, in a position in between or on the sides of our system. So if we put it on the right, which is outside of both the charges, let us see what we have forces. From the first charge, this is the first, this is the second. From the first charge, we have a repulsive force to the right. Again, at every problem, we need to consider our coordinate system and consider the origin. Let us consider the x-axis as our coordinate system and the origin at the second charge. This is what I did in solving this example. Now, if I put it to the right of both charges, I have a force from the first charge repulsive to the right. I have another attractive force from the second charge. So we have two forces, F1 and F2, and the resultant force between them is the subtraction between them. So maybe we have a balance here. Also, if we put it here, we have attractive force from the second charge, F2, and we have a repulsive charge from the first charge, repulsive force to the left. Also here, maybe we have a balance, so we can put it outside. But what if we put it in between the charges? You can see we have a force, repulsive force from the first one to the left, and we have also attractive force from the second charge also to the left. So we cannot find 0 force, so we don't have any balance in between the two charges, because we need to add F1 plus F2, which will not, there is no possibility to have it 0. So we need to consider our position outside of the distribution Q1 and Q2. You can assume it here to the right, you can assume it to the left. I assume it here, I put it to the right, and it's the same. The numbers will tell us the right position. As you see, the distance between Q1 and Q2 is 1. When we need to solve and find the forces between the first charge and the test charge, we need to know how to apply in Coulomb law. We need to know K, we know it. Q1, we know it, which is 2 microcoulomb. We need to know also the test charge quantity, which is 1 millicoulomb. We need to know the distance, which is R. I consider R from the first charge to the test charge. Also, I can assume it from here to here, from the second charge, from the origin. I consider this distance is R from Q1 to the test charge. So the distance from Q2 to the test charge is 1 plus R. Okay? We can use this distance to compute the second force. Now we need to find that the total force F total equals 0. Sometimes we write it like this: summation the forces should be equal to 0. We have just one direction, so this force is in x direction, but it is 0, so there is no direction for this force. Now finding the first force and the second force by using Coulomb law. We know how to do it. We have K, Q1 multiplied by the test charge over the distance square minus the second force, which is K, because we have them in opposite direction. Q2, the test charge, 1 plus R all square. Okay, we need just to find R. We have all the values. Now just take K outside the two terms, which is here as a common factor. Also, the test charge is 1 times -3, which is the millicoulomb. We have the first charge 2 microcoulomb over R square minus 8 times 10 to the -6 over 1 plus R all square. Now the test charge was positive. The negative charge, the negative sign here, because we are subtracting forces. Q2, as you remember, it's negative. We didn't, or we will not put the negative sign for the charge because we already used this bit of information when we determine the forces directions. Okay. Now, also we have micro from the both terms. I take it out to be as a common factor. This is -6. With -3, it will be -9. We have +9 from here, so these will be cancelled. The answer is 1 here. So we have 9. The 2 from here and 2 from here, I take it as a common factor, so we have it 4 here. And we need to unify the denominators. As you see, I can multiply this, the first denominator, by this denominator, and also the same for this term. And we also need to multiply by both of them. We are unifying here the denominator, which is a math step. So we have the common denominator is the same. We have the second term is 8R square, because I multiply by R square. We have here 1 plus R all square. I take 2 from here and here as a common factor, and I have 1 plus R still here alone. We have here 4 because I take the 2 from them. What I can do to solve this, I need to find R. It's math, okay? I can multiply both sides. The left hand side is 0, the right hand side is the values. I can multiply the both sides by this value, which is the denominator in the numerator here, and 2 times 9. When I multiply this value by the left hand side, it will be 0. If I multiply this by this will cancel this, and the 9 with the 2 will be cancelled with the denominator here. So I have the last formula, which is 1 plus R square minus 4r squared equals 0. I just do some reorganization and open the parentheses. So I have the last formula, which is 0 equals 1 plus 2r minus 3r squared. This is second rank equation with one variable, which is r. Remember from math, we can do that. If we have ax squared plus bx plus c equals 0, we can find the value of x using the general method, which is negative b plus minus the square root of b squared minus negative 4ac over 2a. We have positive and negative because we have two values to solve this equation. So one of them is with the positive sign, the other with the negative sign. We will see that now. Now let us apply it to our r. This is our relation. So a is negative 3, b is positive 2, c is positive 1. Apply these values to find r. We have it finally minus 2 plus minus the square root of 16, which is 4, over negative 6. So we have two values, negative 2 plus 4 over negative 6, which is negative third. We have negative 2 minus 4 over minus 6, which is positive 1. These values of r, two possible values. We measure r from the second charge or from the first charge to the right, which is this one. So if we consider the first value, which is negative third, it will be to the left of it. In this case, it will be in between. As we see from the before, we don't have any balance in between. The second one will give us the distance to the right, and that's right. This is the acceptable value. And if we compute the forces at this point, the first force will be 18 newtons to the right, the second force will be 18 newtons to the left, and the resultant force, as you see, 18 minus 18 will be 0. Now we have the same example, but with changing Q2 to the positive charge. As you see here, we have Q2, and I put it at the origin. We have Q1. Again, why we need to put the test charge in between? In this case now, if we have positive charge and another positive charge, and if we put the test charge, which is another positive charge, we have, this is the first, this is the second, we have a repulsive force from the first one to the left, we have a repulsive force from the second one to the right. In this case, we can find balance. But if we put it here, we have a repulsive force from the first one, we have a repulsive force from the second one, we don't have any balance. Both of them will make it accelerate to the right. And the same if we put it at in the left. So the best position is in between. So we can start this solution by putting the test charge in between. We have the total distance from Q1 and Q2 is 1 meter, as you see. We can assume or consider the distance from any one of these charge to the test charge. I consider it here from the second charge to the right. I consider it as R. Now I have, it's a different R than the first one. And the rest, which is the distance from Q1 to the test charge, is 1 minus R. But before, if you remember, it was 1 plus R. Okay? Using the same method, using both terms with Coulomb law, and already I take Q, the test charge magnitude, and the distance, the constant K outside as a common factor. Q is 1 milli, K is the known value. Also we have the macros from Q1 and Q2. I take it as a common factor from here. Again, this with this will cancel 10 to the positive 9. We have the 9. We have 2 and 8. I can take 2 from both terms to be as a common factor. So I had 4. Also, I did unifying denominators. I have 1 minus r squared times r squared here, and 8 or 4 after taking the 2 from it. 4, 1 minus r squared, and here I have 1 after taking the 2 times r squared. Again, to just simplify the things, both terms I will multiply them by this factor. This will cancel this, and 2 9 will cancel 2 9s here. I have it. Finally, I opened the parentheses and reorganize it in this way. So I have 3r squared negative 8 plus 4 equals 0. I used the same relation, which is the general method to find the x value in the second rank equation, polynomial equation. So I have two values of r. The first one is 2 meters. Remember that 2 meters from the Q2, which is here, outside the charge. So there is no balance in our case here, outside the charge. We have also 2/3 of a meter, which is 67 centimeter. This is in between them, because the distance from here to here 1 meter or 100 centimeter. So this is the position where we have a balance. If we compute the first force and the second force, they will be the same with opposite direction, which is 16 or 162 newtons. And as you see here, we have the balance. This problem in 1 dimension. Let us go to another problem which is in 2 dimensions, which has also a different idea than what we have from before. Let us assume this system. We have 3 charges. The first one is 4 microcoulomb. The second one is 3 microcoulomb. And the test charge is Q, which is 2 nanocoulomb. Nano means 10 to the negative 9. Okay, what is the distances? As you see here, I can easily see the XY coordinates at this point. I can assume it as 0 0, which is the origin. And I can see the position of the first charge as 50 centimeters to the positive Y direction, or to the north. And the position of the second charge is 60 centimeters to the south, or to the negative Y direction. And the position of the test charge is 60 centimeter or 0.6 meter to the right, or to the positive X. What I need to know, I need to find the resultant force on the test charge in here. So all of them are positives. So I have repulsive forces. From the first charge, I have a repulsive force to this direction. I can name it F1, as you see it here. From the second charge, I have a repulsive force also in this direction. I can name it F2 easily. How can I find F1 and F2? Easy, by using the Coulomb's law. So the charge, I know them. I need to know the distance. K, it's known, it's a constant. The distance, this is R2 and this is R1. But because I know the other values of this right triangle and this right triangle, I can find R1 and R2 using the Pythagorean theorem. Using that, 50 centimeters, 60 centimeters in meter actually, I can find that R1 equal to 0.78, which is 78 centimeters, and R2 is 85 centimeters. But I need to keep them in the starting unit, which is the meter. Okay, I know the charge, I know K, because Coulomb law, as you know, it's K Q1 Q over, or the test charge here, over R square. I know everything now. I can find any force here. This is the magnitude, but we know from before that the force is a vector quantity. I need to know its magnitude and I need to know its direction. Its direction is easy to be found also by finding or knowing these angles. So the angle of the second force, I consider it as alpha. The angle of the first force is beta. I can find also the values of alpha and beta by using some trigonometry rules, which is tan inverse. Because look here easily, from the first charge and the test charge, we have this right triangle, 50 centimeters, 60 centimeters, and we have this angle beta. Tan beta is 50 over 60, or 0.5 or 0.6, and beta is the tan inverse of this ratio, which is 39.8 degree, which is 0.69 radian. And the same way we can find alpha, which is the tan inverse over 60 over 60, which is 45 degree or 0.785 radians. Okay, now I find the directions. Okay, that's good. Now I have x, y plane. I have two forces, and we know these forces. We will find them now in the next page. And we have the direction of each force. We can find the resultant force by completing the shape. Okay, but also we can find the component of each force. The component of each force, which is the x component and the y component, as you see here. So in the x direction, we have a component of fx, f1, which is f1 cosine theta. I used cosine because I have the angle of that direction. Also I have f2 cosine, not theta actually, this is beta and this is alpha. F2 is the f2 x component is f2 cosine 45 degrees. So we have f2 component and we have f1 component. On the y direction we have two opposite directions. So we have here we need to use the sine. So we have f2 sine theta to the positive y direction, and we have f1 the sine 39.8 to the negative y direction. This is the y component of the first force and the second force. So now we have our forces on the x and y plane. We find their components. Let us see what is the next step. We did this actually just to make our forces on a right triangle, to make computing the resultant force using the Pythagorean theorem and the trigonometry relations easier. But also we can find the resultant force by completing the shape here. It will be this force, for example, depending on the magnitude of the forces. I am drawing now. I need to give you an idea that I'm drawing them with equal lengths because I don't know the magnitude of them, but maybe one of them is long, one of them is short because their magnitude is big or small. I don't know that yet. Okay, let us find f1 and f2. We have r1 and r2 using the Pythagorean theorem previously, and applying in the Coulomb law for both forces, we can find the first force is 1.18 times 10 to the negative 4. We have the second one is 7.47 times 10 to the negative 5 newtons. And we have the angles. We need to use the sine and cosine as we find here. So just let us write them. Sine alpha, which is this, which equals also the cosine for the 45 degrees, and sine beta equals this value, and the cosine equals this value. We will use them now. Now for all the components, look, for those components on the x-axis, we need to add them together because both of them are in the same direction. But for the y components, they are in opposite direction, so we need to subtract them because they have different opposite direction. Okay? For the x component, we just add the first one and the second one. This is the x component. We have the first force component, the second force component, which is the first force times cosine theta, or times cosine beta in this case, and the second force times cosine alpha. This is the resultant force in x direction. And the same we have, I take F1 direction minus F2 direction. You can do that. And the direction, the final direction, is to the direction of the biggest one. So I use it. F1 component minus F2 component, using the sine with the angles. That resultant force in y direction is 2.29 times 10 to the negative 5. As you see here, this one is bigger because it's to the negative 4. If we maybe sometimes we have a balance because we have opposite directions. Now let us go further and draw our forces. For F1, it's 1.44 times 10 to the negative 4, which is 14 times 10 to the negative 5. The second force is 2.29 times to the negative 5, 10 to the negative 5. As you see, the first force, or the x component force, is 14. Here it is 2. Means that this force in x component is 7 times almost than the first one, which means this force should be longer. So the resultant force will be in this direction. The resultant force, using the Pythagorean theorem, is fx squared plus fy squared, which is, after solving this, it will be 1.56 times 10 to the negative 4 newtons in magnitude. This is the magnitude. And the direction, we need to find the angle theta. The angle theta by using tan inverse of fy over fx. This is fx. Then it will be tan inverse of the forces, the ratio of the forces. It will be 80.95 degrees, almost 81 degrees. This is the direction. And this angle is taken below the x-axis. In this case, we found the magnitude and the direction of the resultant force in 2 dimensions. That's all. In the next sections, we will deal with the electric field. We will see some examples look similar to these, and it will be very useful. Thank you.